Welcome to the Sleepy Professor. Tonight, we will be talking about something truly fascinating, the science of time travel. Is it possible? What does physics say? And how far can imagination stretch before it becomes reality? Close your eyes, get comfortable, and let's drift through time together. What if I told you that time, this invisible force that shapes every moment of your life, might not be what you think it is? That the ticking of the clock, the rhythm of days and nights, might only be one version of reality? Time feels so obvious. It flows, second by second, minute by minute, from the past to the future. We live inside it, plan around it, measure it with calendars and watches, and yet, when scientists look deeper, time becomes one of the most mysterious, slippery concepts in the entire universe. From the moment we wake up to the moment we fall asleep, time frames everything we do. It gives structure to our days and a sense of direction to our lives. But where does it come from? And why does it move the way it does? Ancient civilizations watched the sun rise and fall, marked the seasons, and followed the movement of stars. For them, time was tied to nature. The Egyptians divided the day using sundials. The Mayans built vast temples to align with celestial events. The Chinese created incredibly detailed lunar calendars. For thousands of years, time was measured by the sky, but even then, people wondered what it really was. Fast forward to modern science, and the questions haven't gone away. If anything, they've grown deeper. Time isn't something you can hold or touch. It has no color, no weight, and yet it affects everything. We age, we remember, we anticipate. Without time, nothing would change. No motion, no history, no future. But physicists today see time not as a force or a flow, but as a dimension, just like up and down, left and right, forward and backward. In this view, time is woven into the very fabric of space. It's part of the four-dimensional structure called space-time, and we're moving through it every second of our lives. But here's the twist. Time might not be a river that flows. That idea of time as a current carrying us forward might be an illusion, something our minds create to make sense of cause and effect. Physicist Julian Barber once proposed that time doesn't really flow at all. Instead, he suggested that the universe is made up of countless still moments, like frames in a film strip. We don't travel through time. We jump from one frame to the next, and our memories give us the illusion of motion. Each moment, according to this idea, exists on its own. Past, present, and future, all laid out like snapshots in a cosmic photo album. What we call now is just the frame we're experiencing. And then there's entropy, the idea that the universe moves from order to disorder. Pour cream into coffee, and it swirls into beautiful patterns, then settles into one uniform color. But you never see it separate again. This direction, from less entropy to more, is the arrow of time. It's why we remember yesterday but not tomorrow. It's why broken glass doesn't unshatter. But no physical law says time has to move forward. On paper, the equations of physics work just as well backward as they do forward. The universe doesn't seem to care, yet we do. Time is deeply personal. When you're waiting, it crawls. When you're joyful, it flies. It bends with emotion. It feels different in dreams. It disappears in sleep. It stretches and shrinks, depending on how we experience it. And that subjective side of time is just as important as the scientific one. Because no matter how many theories we come up with, we live time from the inside. It carries our stories, our hopes, our regrets. And maybe, just maybe, it holds the secret to traveling beyond the present moment. So tonight, as you lie still and listen, remember this: time may not be as steady as you think. Beneath the ticking of clocks and the setting of suns, there may be something stranger, something more fluid, more flexible, and more mysterious than anything we've yet imagined. And if time isn't what it seems, maybe time travel isn't just possible, maybe it's already happening. Imagine a world where everything runs in reverse. Raindrops leap off the ground and fly back into the sky. Broken cups reassemble themselves on kitchen tables. Smoke funnels down through the air and settles neatly back into a cigarette. It sounds absurd, even impossible. And yet, according to the fundamental laws of physics, there's nothing in the math that says this couldn't happen. The equations that govern how particles move, how forces act, and how light travels all work just as well backward as they do forward. So why, in the real world, do we only experience time going in one direction? This question is at the heart of one of the most puzzling concepts in science, the arrow of time. It's what gives our lives structure. We are born, we grow older, and eventually, we fade. We remember the past, but never the future. We can relive memories, but we can't pre-live them. Everything seems to move forward, from the smallest seedling stretching toward the sun to the expanding universe itself. But what gives time its direction? Why can we walk across a room, but not across time? To answer that, scientists often turn to the concept of entropy. At its core, entropy is a measure of disorder. Picture a child's bedroom. In the morning, it might be neat and tidy, everything in its place. But as the day goes on, toys are scattered, books pile up, clothes end up on the floor. It's not that anyone planned for it to become messy, it's just what tends to happen. Order turns into chaos. This is the natural trend of things. And in the world of physics, this principle is embedded in the second law of thermodynamics. In a closed system, entropy always increases. That single law may be the key to understanding the arrow of time, because it's the only law in physics that has a direction. Everything else is time symmetric. If you filmed 2 billiard balls colliding and played the video in reverse, you wouldn't be able to tell if the tape was running backward. But if you showed a glass shattering or an egg scrambling itself mid-air, the direction of time would be obvious. You'd know instantly that something was off. That's entropy at work. Now think about the entire universe. Scientists believe it began in a state of incredibly low entropy, a highly ordered, tightly packed singularity. Over billions of years, stars formed, galaxies spun into shape, and the universe expanded. And with each passing moment, entropy increased. The universe grew more complex, more spread out, more disordered. This gradual rise in entropy could be what gives time its forward push. It's as if the universe started a stopwatch when it exploded into existence, and ever since, it's been moving steadily toward more chaos. But that leads to another mystery. Why did the universe begin in such a low entropy state to begin with? Out of all the possible ways things could have started, why did it begin so neatly? Some physicists believe this question touches on the edge of what we can know. Others think it might reveal deeper laws of physics we haven't discovered yet. It could even suggest the existence of other universes, some where time flows differently, or not at all. There's also the human experience to consider. We live time emotionally, not just mathematically. We feel it, we dread it, or treasure it. It shapes how we understand cause and effect. If you knock over a vase, it breaks, never the other way around. But if we could step outside ourselves, outside our biology and our memories, would we still sense the same direction? Or would time become something else entirely? Maybe, in some distant future or alternate realm, the arrow could flip. Maybe there are places or conditions where time circles back on itself, loops endlessly, or even stands still. For now, we live in the forward flow, but the more we study time, the more we realize it's not just a passive backdrop. It has rules, quirks, and perhaps even secrets. And somewhere within those secrets, hidden in the rise and fall of entropy, lies the path to understanding whether we are truly passengers on a one-way ride, or explorers who might one day learn to turn around. At the dawn of the 20th century, one man quietly reshaped the way we understand the universe. In 1905, a young patent clerk named Albert Einstein published a series of papers that would change everything. Among them was his special theory of relativity, a radical idea that not only redefined space and motion, but time itself. Before Einstein, time was thought to be absolute. A ticking clock was the same for everyone, everywhere. Time marched forward with a steady, universal rhythm. But Einstein saw something entirely different. He realized that time is not fixed. It bends, stretches, and slows depending on how you move and where you are. Suddenly, time was no longer a universal constant. It was personal, different for each observer, woven together with space to create a single, fluid fabric, space-time. Einstein's insight began with a simple, elegant idea. The speed of light is the same for everyone, no matter how fast they are moving. This might not sound revolutionary, but it leads to astonishing consequences. Imagine you're on a train moving close to the speed of light, and you shine a flashlight forward. You would see the beam of light move away from you at the normal speed of light, but someone standing still beside the tracks would also see that same beam moving at the same speed. For this to work, something else must adjust, and that something is time. The faster you move, the slower time passes for you, relative to someone who is standing still. This isn't just a trick of perception. It's real, it's measurable, it's been confirmed again and again through experiments. Time literally stretches. This effect is known as time dilation, and it's one of the key pillars of relativity. The faster you go, the more time slows down. If you could travel close to the speed of light and then return to Earth, you would find that more time had passed for everyone else than for you. Days might have gone by for you, while years, decades, could have passed on Earth. It's not just theoretical. We see it in action with high-speed particles, which live longer than expected simply because they're moving so fast. We see it in astronauts who spend time in orbit and return just a fraction of a second younger than those who remained on Earth. Time doesn't move at one speed for everyone. It's flexible, responsive, and deeply tied to motion. But this idea didn't stop at speed. A few years later, Einstein expanded his theory to include gravity. In general relativity, he showed that massive objects like planets and stars warp the fabric of space-time. This warping affects how time flows. The stronger the gravitational field, the slower time moves. This means that time ticks ever so slightly slower at the surface of the Earth than it does high above it. It means that time moves slower near a black hole than it does in open space. If you stood near the event horizon of a black hole, carefully avoiding being pulled in, you could theoretically watch the universe fast forward around you. Galaxies could age, stars could die, civilizations could rise and fall in what feels like moments. Einstein's theories opened a doorway, not just to understanding time, but to manipulating it. He gave us a model of the universe, where time is dynamic, where motion and gravity shape the tempo of existence. And while we haven't yet built machines that can leap centuries into the future, the rules, the very foundation, suggest it's possible. Time travel, at least in one direction, is already a reality. Every second you move, you're shifting through time at a slightly different rate depending on your motion and gravity. It's subtle on human scales, but undeniable. And perhaps most astonishing of all is that these ideas began not in a lab, but in the quiet mind of a man, imagining what it would feel like to chase a beam of light. That thought experiment, so simple, so childlike in its curiosity, led to one of the most profound revolutions in science. Einstein didn't invent time travel, but he gave it credibility. He showed us that time is not the rigid metronome we once believed. It can twist and stretch, it can slow down, and if it can do all that, what else might be possible? In the ripples of relativity, we find not only the blueprint for the future, but the first real steps on the path to traveling through time itself. We often think of time travel as something that belongs in science fiction, a grand, dramatic leap into the future aboard sleek spacecraft, or a sudden flash that sends someone hurtling into the past. But the truth is, time travel is already happening, not in the way the movies portray, perhaps, but in tiny, measurable, undeniable ways, right here on Earth. Every single day, time moves differently for different people, depending on how fast they're going and where they are. It's not fantasy, it's physics. The most practical example of this is orbiting above us right now, quietly circling the planet, assisting us with navigation, maps, and timing, the GPS satellites. These satellites aren't just beacons broadcasting location data, they're incredibly precise clocks, ticking in orbit, high above Earth. And those clocks don't tick at the same rate as clocks on the ground. Why? Because they're moving faster, and they're farther from Earth's gravitational pull. According to Einstein's theories, both special and general relativity, this changes the flow of time. The high speed of the satellites slows their clocks down, while the weaker gravity speeds them up. The two effects don't cancel each other out perfectly. In fact, if we didn't account for these time differences, just a few billionths of a second every day, GPS systems would quickly become useless, off by miles within a single day. To keep things accurate, engineers have to correct for the effects of time dilation. In essence, they're adjusting for time travel. Think about that for a moment. Every time you check a map on your phone or navigate to a new place, you are relying on a technology that works only because we understand how time bends and stretches under different conditions. Time dilation isn't just real, it's built into the infrastructure of our modern world. But GPS satellites are just the beginning. The same principles apply to astronauts aboard the International Space Station. They orbit Earth at roughly 17,500 miles per hour. While they're up there, time ticks just a bit more slowly for them compared to people on the surface. The difference is minuscule, fractions of a second, but it's enough to be measured. If an astronaut spends 6 months aboard the station, when they return, they will have aged ever so slightly less than their friends and family on Earth. It's not enough to notice in daily life, but it's proof that the faster you move, the slower time passes. Now imagine scaling this up. What if we could travel at speeds close to the speed of light, the ultimate cosmic speed limit? The effects would become extreme. A journey that lasts just a few years for the traveler could mean centuries passing back on Earth. Time dilation would stretch the experience so dramatically that it would feel like leaping into the future. And all of it follows directly from Einstein's equations. No magic, no speculation, just the strange and elegant reality of how time behaves. We're also learning how incredibly sensitive time really is. Scientists have developed atomic clocks so precise that they can detect differences in time based on just a few feet of altitude. Move one clock slightly higher on a shelf, and it ticks faster than the one below. This means that people living on mountaintops are aging, very slightly, faster than those at sea level. Over a human lifetime, the difference is trivial, but it's there. And the more precisely we can measure time, the more clearly we see its flexibility. It's not the rigid universal force we once believed. It bends and flows depending on motion and mass. All of this invites a profound realization. We are already living in a world where time doesn't move the same for everyone. It isn't fair or equal. It's curved, shaped by speed and gravity. Every person is, in a sense, in their own unique bubble of time. And although we tend to experience time in a shared rhythm, sunrise, sunset, seasons, clocks ticking on walls, the underlying truth is far stranger. Our lives are unfolding on slightly different timelines, imperceptibly drifting apart, shaped by where we are and how we move. It's humbling, and it's exhilarating, because if such subtle time travel is already happening, then the doorway to more dramatic time journeys may not be as distant as we think. We've already learned how to measure time's elasticity. The next step may be learning how to stretch it deliberately, to step into the river of time and move through it by design. The seeds of that journey are already planted, in satellites above us, in clocks on mountaintops, and in the quiet awareness that time is not a single, ticking metronome, but a living, changing thing. Close your eyes and imagine drifting through the cold, silent void of space. Stars shimmer in the distance, like frozen sparks, scattered across an endless black sea. Ahead of you looms something strange, something massive, a sphere so dark it seems to absorb light itself, a black hole. At first glance, it looks like a shadow, a hole in the fabric of reality. But this isn't just empty space. This is one of the most extreme and fascinating objects in the universe. A black hole is what remains when a massive star collapses under its own gravity, compressing into an object so dense, so heavy, that its gravitational pull becomes almost infinite. Nothing, not even light, can escape it, and near it, time begins to behave in ways that challenge everything we think we know. As you draw closer to the edge of this strange object, you're approaching what scientists call the event horizon, the boundary beyond which nothing can return. But something extraordinary happens as you near this threshold. From the perspective of someone watching you from far away, your motion seems to slow down. You appear to move in slow motion, your ship inching toward the event horizon with infinite slowness. Minutes stretch into hours, hours stretch into days. Eventually, you seem to freeze in place, caught forever at the edge of the void. But inside your ship, time feels normal. Your heart beats, you breathe, you think. The closer you get to the event horizon, the more time slows down, for you, relative to the outside universe. This isn't a science fiction fantasy. This is a real prediction of Einstein's general theory of relativity. Gravity doesn't just pull on objects, it pulls on time itself. The more massive the object, the more dramatically it warps the flow of time around it. And black holes are the most massive, most compact things we know of. Their gravity is so intense that they don't just slow time, they twist it, stretch it, bend it into strange new shapes. To us, time flows forward steadily, but near a black hole, time stretches like taffy. If you could hover just outside the event horizon and then somehow escape, you might find that decades or centuries had passed elsewhere, while you had only experienced a few hours. In fact, if you were to orbit a black hole at just the right distance, a safe path called the innermost stable circular orbit, you could use its gravity to move through time. You wouldn't notice anything strange while you circled, but if you returned to Earth, it would feel like stepping into the future. You'd find a changed world. New buildings, new generations, new histories. You would be a traveler who left and came back to find the world aged without you. The black hole, by slowing time in your local frame of reference, would have made that journey possible. No flux capacitor, no time machine, just gravity and the relentless stretching of space-time. But black holes do more than just bend time. They represent some of the deepest mysteries in physics. At their cores, hidden behind the event horizon, is a region called the singularity, a point where density becomes infinite, and our current understanding of the laws of nature breaks down. Time and space cease to behave in any predictable way. Some scientists believe that inside the singularity, time may even stop altogether. Others suggest that the rules may flip, past and future becoming jumbled, cause and effect unraveling. It's a region of mystery we can't yet penetrate, because no information can escape it. Anything that crosses the event horizon is lost to us forever. And yet, black holes are not just destroyers. They might also be gateways. Some physicists have speculated that black holes could be linked to something called white holes, hypothetical objects that do the opposite. They push matter out instead of sucking it in. If the universe contains both, and if a black hole and a white hole are connected through space-time, the result would be a tunnel, a shortcut, a wormhole, a bridge between distant points in the universe, or perhaps even different times. It's purely theoretical. We've never seen a white hole, but the mathematics suggests it's not impossible. Even more intriguing is the idea that black holes may preserve information in some form. According to quantum mechanics, information can't be destroyed, not even by a black hole. This has led to a paradox that remains one of the greatest puzzles in physics. What happens to the information carried by the things that fall in? Does it disappear forever, or is it somehow encoded in the surface of the black hole, like data on a cosmic hard drive? If we could understand this, we might gain a deeper insight into the nature of time itself, how it stores events, and whether those events can be recovered or reversed. So the next time you gaze up at the night sky, remember that out there, hidden among the stars, are places where time is twisted beyond recognition, places where the ticking of the cosmic clock slows to a crawl, places where, with the right path and a bit of luck, the future could be reached more quickly than we ever imagined. Black holes are more than just gravitational monsters. They are nature's time machines, dark and mysterious windows into the deepest possibilities of our universe. Imagine two twins, identical in every way. They are born on the same day, grow up side by side, share the same experiences, the same laughs, the same moments. But one day, one of the twins is chosen for a special mission. She will travel into space on a high-speed journey aboard a spacecraft capable of approaching the speed of light. Her twin stays behind on Earth, continuing life as usual, grounded in the familiar rhythms of our planet. The spaceship launches, cutting through space like a silent arrow, accelerating to incredible speeds. For the twin on the ship, time seems to flow normally. Her heart beats, her thoughts drift, her days unfold, just as they always have. But what she doesn't notice is that time outside her craft, on Earth, in the rest of the universe, is moving faster. This is the heart of the twin paradox, one of the most famous thought experiments in physics. It's not just an idea, it's a consequence of Einstein's theory of special relativity, and it's backed by real science. According to relativity, the faster you move, the slower time passes for you, relative to someone who is not moving with you. It's not an illusion or a trick of perception. It's a measurable, physical effect. So while the spacefaring twin experiences, let's say, 5 years aboard her ship, her sibling on Earth might experience 10 or 50 or even more, depending on how close the ship came to the speed of light. When the twin finally returns home, she steps off the ship and sees a different world. Her twin is older, perhaps significantly older. Her friends have changed, the world has changed, and she has become, quite literally, a traveler through time. What makes this paradox so compelling is that it's both strange and beautifully simple. The symmetry of the twins is broken not because one was simply moving, but because one underwent acceleration, left, turned around, and came back. That journey through the curves of space-time changed her path through time itself. In a way, it's like taking a shortcut across the surface of a vast landscape. While the twin on Earth walked a slow, steady path across the hills, the other was flung across a high arc, curving through time at a different angle. And when the two paths meet again, the difference is not theoretical, it's physical. It's written into their bodies, their ages, their memories. This phenomenon has been demonstrated on a much smaller scale, with real-world experiments. Highly accurate atomic clocks placed aboard fast-moving jets or satellites have returned ticking slightly slower than identical clocks on the ground. We're not just talking about milliseconds, we're talking about nanoseconds and microseconds, measured with astonishing precision. But the principle is exactly the same. Motion through space affects motion through time. Time is not fixed, it stretches and shrinks, depending on your journey. The twin paradox isn't just a curiosity. It raises deep questions about how we experience time, and whether time is something we travel through like a road, or something we carry with us like a personal atmosphere. Each of us is moving through space-time at our own unique angle, determined by our speed and position in the gravitational web of the universe. And while the differences are almost too small to notice in our everyday lives, they are always there. Tiny divergences, quiet separations. Now imagine scaling this up, not just with two people, but with civilizations. Imagine future explorers venturing out to the stars, taking journeys that, for them, last a few years, but for Earth, span centuries. Imagine returning to a homeworld filled with unfamiliar faces, strange technology, cities built atop the ruins of the old, languages evolved, cultures shifted. Time travel, in this sense, doesn't need paradoxes or magic doors. It only needs speed, distance, and patience. And yet, at the heart of this concept is something profoundly human, the idea of leaving behind what you know, only to return and find it changed. The twin paradox is not just a scientific model. It's a story of separation, of discovery, of transformation. It reminds us that time is not something we observe from the outside. It's something we live, something we carry, and when we stretch it, bend it, or race through it, we're not just measuring numbers, we're rewriting our place in the story of the universe. In the stillness of night, when you consider the vast distances and the deep silence of space, remember that time, too, is a landscape. And somewhere out there, perhaps not too far from now, someone might already be on their way, drifting through time, carried forward by motion alone, bound to return to a future none of us can yet imagine. Imagine for a moment that space is not empty but flexible, like a vast sheet of fabric stretched out in all directions. Every star, planet, and galaxy is resting on that fabric, bending it ever so slightly with their weight, warping the shape of space and the flow of time. Now picture folding that sheet in half, bringing two distant points together so that they touch, and then puncturing a hole through both layers, creating a tunnel, a bridge, a secret passage. That's the idea of a wormhole, a shortcut through the cosmos, a tunnel not just through space, but through time itself. Wormholes, sometimes called Einstein-Rosen bridges, emerged from the mathematics of general relativity, Einstein's great theory that describes gravity not as a force, but as the curvature of space-time. In 1935, Einstein and physicist Nathan Rosen found that the equations of general relativity allowed for these strange connections between distant parts of the universe. At first, it seemed like a mathematical curiosity, an odd feature of an otherwise elegant theory. But as physicists studied these equations more closely, something remarkable became clear. If wormholes were real, if they could somehow be made stable, traversable, they might allow for instant travel between faraway galaxies. And even more astonishing, they might make time travel possible. The idea works like this. Imagine one end of a wormhole placed on Earth, and the other end placed on a spaceship traveling at near the speed of light. As we've seen in the twin paradox, time slows down on fast-moving ships. If the ship and its wormhole mouth return to Earth after a long journey, the two ends of the wormhole would be out of sync. One would be anchored in the past, the other in the future. And if you could step into the wormhole from the future side, you could emerge in the past. The tunnel through space would also be a tunnel through time. But there's a catch, or rather, several. Wormholes, if they exist at all, would be unstable. In theory, they would collapse almost instantly under their own gravity, pinching shut before anything, or anyone, could pass through. To keep one open, you'd need something exotic, something not found in everyday life, something called negative energy. Not just low energy, negative energy, a strange concept predicted by quantum physics. It would act as a kind of anti-gravity, pushing space apart instead of pulling it together. If such a substance could be harnessed, it might prop the wormhole open, creating a traversable passage through space-time. But we've never observed large amounts of negative energy, and we don't yet know if it's even possible to manipulate it the way wormholes would require. Still, the theory persists because the math says it could work, and that math, grounded in Einstein's field equations, continues to be one of the most rigorously tested frameworks in science. Wormholes may not just be fantasy, they may be rare, exotic features of the universe that we've yet to detect. And if they exist, the implications are staggering. A wormhole could link two galaxies millions of light years apart. It could allow travelers to skip across vast stretches of the cosmos in seconds. It could permit communication across centuries. It could turn the past and future into neighboring rooms. But there are deeper, more mysterious questions too. If time travel through a wormhole were possible, what would it mean for causality? What happens if you go back in time and change something important? Could paradoxes emerge? Could you stop yourself from ever entering the wormhole to begin with? Some physicists argue that the universe would find a way to correct itself, to preserve consistency. Others suggest that each trip backward might create a new timeline, a branching path where events unfold differently, a multiverse of possibilities. There's also the question of stability, not just physical but informational. Could you send a message through a wormhole? Could you glimpse tomorrow's headlines? Could knowledge of the future influence the past in dangerous or unintended ways? Even the simplest communication across time invites a cascade of consequences. And yet, these questions are not just philosophical. They are being asked, debated, modeled, and studied by physicists around the world. The idea of a wormhole, elegant and terrifying, remains one of the most tantalizing concepts in theoretical physics. It brings together the vastness of space, the mystery of time, and the strange counterintuitive logic of the quantum world. And whether they remain forever theoretical or one day become real tools for exploration, wormholes have already achieved something remarkable. they've stretched our imaginations. They've shown us that the universe might be more connected, more flexible, more astonishing than we ever dreamed. So if you ever find yourself staring at the night sky, wondering what's really out there, remember, the stars you see may not be as far as they appear. Somewhere, buried deep in the folds of space and time, a shortcut might already exist, a tunnel waiting to be discovered, leading not only to another place, but perhaps to another moment in time. Now imagine, for just a moment, that time travel has become possible. Through some brilliant scientific breakthrough or a strange cosmic anomaly, you've discovered a way to step backward in time. Not just to observe the past, but to move through it, to walk its streets, to breathe its air, to interact with it. And in this incredible moment of opportunity, a thought enters your mind, something as curious as it is dangerous. What if you could change something? What if you could alter the past? What if, just for the sake of experiment, you traveled back far enough to prevent the very conditions of your own existence? This is the heart of the grandfather paradox, a puzzle so elegant, so deeply unsettling, that it has haunted physicists and philosophers for generations. The scenario is simple. Suppose you go back in time and prevent your grandfather from meeting your grandmother. Maybe you accidentally interfere with their meeting, or more drastically, you remove him from the timeline altogether. If that happens, your parent would never have been born. And if your parent was never born, then neither were you. But if you were never born, how did you travel back in time in the first place? And if you didn't, then your grandfather was never stopped, and your family line continues. But then, you did exist. You did travel back. The cycle loops again and again, with no clear resolution. This paradox strikes at the very foundation of causality, the idea that every effect must have a cause, that time flows in a chain of events, each one leading to the next. When we imagine changing the past, we unravel that chain. We reach back into the sequence and try to snip a link, forgetting that the entire structure depends on the very link we're cutting. It's like standing on a branch and sawing it off from the trunk. The moment you succeed, you fall. And yet, if you fall, you never climbed the tree to begin with. Some scientists and thinkers have tried to resolve the paradox by suggesting that the past is fixed, that no matter what we do, events will always unfold in such a way that the timeline remains intact. You might try to stop your grandfather, but something will always intervene. Bad timing, a coincidence, a twist of fate. You'll stumble, change your mind, or simply fail, and history will continue unbroken. In this view, the universe is self-consistent. It protects itself from contradictions, as if reality has a built-in immune system that prevents time travelers from rewriting its code. Others take a different approach. They suggest that the moment you change something in the past, you don't rewrite your own timeline. You create a new one, a branching path, a parallel universe. In this multiverse model, your interference spawns a different version of history, one where you were never born, while the original timeline, the one you came from, remains untouched. You haven't destroyed your own existence, you've simply moved into a reality where you no longer exist. The paradox dissolves, not by avoiding contradiction, but by expanding the number of possible outcomes. There's also a quantum perspective. In the strange world of quantum mechanics, particles can exist in multiple states at once until they are observed. Some physicists have speculated that time itself might behave similarly, that multiple outcomes could coexist in a sort of temporal superposition, only becoming fixed when they intersect with consciousness or observation. If time travel works on a quantum level, perhaps it follows different rules entirely, rules that don't depend on single linear timelines, but on probabilities and entangled realities. It's an eerie thought, but it might help explain how the universe avoids logical dead ends. And yet, for all these theoretical solutions, the grandfather paradox remains a powerful reminder of how fragile our assumptions about time really are. We treat it as something straightforward. Yesterday leads to today leads to tomorrow. But the moment we try to reverse that flow, everything becomes uncertain. The paradox forces us to ask uncomfortable questions. Is the past unchangeable? Is free will an illusion? Are all our choices already woven into the fabric of time? Or is the universe far stranger than we imagine, with multiple versions of history, each spinning out from a single decision? Ultimately, the paradox doesn't need to be solved to be meaningful. Its power lies in what it reveals, that time is not just a backdrop for events, but a living, dynamic force filled with tension and complexity. If we ever do find a way to move through time, we may have to accept limits, not because of technology, but because of logic. Not everything that can be imagined can be done. Or perhaps we'll discover new rules, deeper truths, hidden beneath the surface of what we call time. So as you drift towards sleep, imagine this strange possibility that every choice you've ever made has spun a new thread of reality. That in some distant branch of the cosmos, a different version of you is walking a different path. And maybe, just maybe, one of those paths is looping backward, searching the past for answers, trying to find its way home. Close your eyes and step into the smallest world imaginable, the realm of the quantum, where particles blink in and out of existence, where matter dances in uncertainty, and where the rules of classical logic seem to dissolve into a strange probabilistic haze. Here, reality is not solid or fixed, but fluid. A particle can be in two places at once. It can spin in opposite directions simultaneously. It can tunnel through barriers that should be impassable. It can be nowhere and everywhere. In this world, time becomes not a steady river, but a shimmering sea of possibilities. And it is here, in the uncertain whispers of the quantum world, that new ideas about time travel begin to take root, not through massive machines or black holes, but through probability, entanglement, and the bizarre power of possibility itself. In classical physics, everything is predictable if you know the starting conditions. A ball tossed into the air follows a clear path. A planet orbits a star with precise motion. Time flows neatly from cause to effect. But in quantum mechanics, things work differently. A particle doesn't have a definite location or momentum until it's observed. Until that moment, it exists in a superposition, a cloud of all possible states. Only when you measure it does it collapse into a single outcome. It's as if the universe waits for you to look before deciding what to become. And the deeper scientists dig into quantum theory, the more it seems that time itself might be governed by similar principles. Perhaps the future isn't written. Perhaps it doesn't even exist until we reach it. Some interpretations of quantum mechanics, like the many worlds interpretation, suggest that every possible outcome of every quantum event actually does occur, but in a separate, branching universe. If that's true, then time doesn't unfold as a single thread. Instead, it splits endlessly, branching into a multiverse of possibilities. Every decision you've made, every path you didn't take, every word you chose not to say, each might exist in its own timeline, running parallel to this one, each as real as the reality you know. If time travel were possible through this lens, it might not mean traveling to your past, but to a version of the past in a neighboring timeline. You wouldn't change your own history. You'd simply slide into a new one. You'd walk through the doors of another world where things happen differently. And then there's entanglement, a phenomenon Einstein famously called spooky action at a distance. When two particles become entangled, their properties remain connected, no matter how far apart they drift. Change one, and the other responds instantly, as if they are still part of the same system. This connection seems to defy space, to ignore distance, and some physicists wonder if it might also ignore time. Could information be sent between entangled particles, not just across vast distances, but across different moments in time? Could quantum entanglement create a kind of communication between past and future? Experiments haven't yet proven this, but they hint at something profound, that time, at the quantum level, might not be as linear or as separate as we experience it in daily life. There are also theories in quantum gravity, attempts to reconcile quantum mechanics with general relativity, that propose time might not be fundamental at all. That is, time might not be a basic building block of reality, but something that emerges from deeper, timeless laws. In these models, time could be a byproduct of entangled relationships between particles, a kind of illusion created by the unfolding of interactions. If true, this would mean that time is not an arrow, but a shadow, a pattern that only seems to move forward because of how we're built to perceive it. And if time is emergent, then so is the idea of a past or future. That would radically change the way we think about time travel. Instead of moving through a fixed medium, we might be able to manipulate the very pattern itself. Then there's the transactional interpretation of quantum mechanics, a lesser-known but deeply fascinating idea. It proposes that particles don't just travel forward in time, but also backward. That every quantum interaction involves a handshake between the past and the future, a kind of bid and response across the temporal divide. In this view, the future is not just shaped by the past is shaped by the future. It's a kind of dialogue between moments, a hidden conversation woven into the fabric of reality. If this is true, it suggests that events might not be strictly bound by the direction of time as we perceive it. There could be a give and take between moments, where cause and effect ripple in both directions. None of these theories offer a clear roadmap for building a time machine, not yet, but they do suggest that time may not be as rigid, as absolute, as we've long believed. At the quantum level, the flow of time may be more like a shimmer than a stream, more like a cloud of maybes than a line of certainties. And if that's true, then perhaps the boundaries of past, present, and future aren't as firm as they seem. Perhaps what we call the future is a canvas still waiting for its first brushstroke. Perhaps the past isn't gone, but folded into the present in ways we haven't yet learned to see. So tonight, as your thoughts slow and your breath deepens, let yourself drift into the strange and beautiful uncertainty of the quantum world, a place where time has edges that blur, where moments branch like trees in a forest of possibility, where each second might contain countless futures. And maybe, in one of those futures, we've already found the key to moving through time, not by force, but by understanding the gentle, whispering language of the universe's smallest parts. For centuries, the idea of a time machine has captured human imagination. From ancient myths to modern fiction, we've dreamed of building something, a device, a structure, a vessel that could carry us across the timeline of history, like a ship sailing through the ocean. While we often picture time machines as whirring gadgets with glowing gears or spinning dials, science has taken the idea more seriously than you might expect. In fact, deep within the realm of theoretical physics, scientists have been quietly exploring the question, what would it take to construct a real, working time machine? And the answers, while complex, are not entirely ruled out by the laws of nature. One of the first serious proposals came from a brilliant Dutch physicist named Willem Jacob van Stockum in 1937. Building on Einstein's general theory of relativity, he studied the effects of rotating matter on the fabric of space-time. What he discovered was remarkable. If you took a cylinder of matter and spun it fast enough, close to the speed of light, it could twist space-time around it in such a way that a closed loop in time might be possible. Essentially, an object moving through this twisted space could follow a path that returns it to its own past. This hypothetical path is called a closed time-like curve. In theory, it would be like walking in a circle, not in space, but in time. Van Stockum's rotating cylinder was purely theoretical, but it was one of the first blueprints for a time machine grounded in physics rather than fantasy. Later, in 1974, another major contribution came from Frank J. Tipler, who proposed an infinite cylinder of incredibly dense matter, again spinning at near light speed. Known as the Tipler cylinder, this structure, if it could be built, would also allow for closed time-like curves. The idea was that the rotation would drag space and time around it, enabling you to spiral backward through time. But the catch, of course, is that it would have to be infinitely long, or at least as long as the universe itself. And even if we could somehow build it, the stresses involved would likely collapse the structure into a black hole before anything useful could be done with it. Still, the mathematics held. The door remained open. Then came Kip Thorne, a name closely tied to the concept of wormholes. In 1000, 988, Thorne and his colleagues began exploring whether wormholes, those hypothetical tunnels through space-time, could be used for time travel. The idea was simple in concept but stunning in implication. Take a wormhole and move one end at a high speed, perhaps by placing it on a fast-moving spacecraft, and then bring it back. Because of time dilation, the moving end would age more slowly than the stationary one. If the wormhole remained open and stable during this journey, someone stepping through it could move from one time to another. You could enter the wormhole in 2200 and emerge from the other end in 2100, essentially traveling back in time, or the reverse, leaping centuries into the future. The concept was sound within relativity, but again, the obstacle was practicality. Keeping a wormhole open would require negative energy or exotic matter, materials that we don't yet have access to, or perhaps don't even exist in usable forms. Another intriguing model comes from the work of Israeli physicist Amos Ori, who in 2005 proposed a theoretical time machine that doesn't rely on exotic matter, but rather on the curvature of space-time itself. In Ori's design, a massive donut-shaped structure made of conventional matter could manipulate space-time to create a closed time-like curve. His equations showed that such a structure might allow travel back and forth in time within a limited region, assuming we could control the curvature precisely. The appeal of Ori's model was that it avoided the need for negative energy, suggesting that time travel might not require violating known physics, only pushing them to their extremes. And yet, as creative and mathematically sound as these models are, each one confronts serious challenges. Stability, energy requirements, quantum effects, and causality concerns all cast long shadows over the dream of a functioning time machine. Some scientists argue that even if closed time-like curves are mathematically possible, the universe may have built-in safeguards to prevent them. Theoretical physicist Stephen Hawking famously proposed the chronology protection conjecture, which suggests that quantum effects would always act to destroy any structure capable of permitting time travel, thereby preserving the logical order of events and preventing paradoxes. In essence, the universe might protect itself from the contradictions that time travel would create, sealing up any loopholes before they can open too wide. Despite these barriers, research into time machines continues, not because we expect to build one tomorrow, but because asking the question teaches us something profound about the universe. When we study what it would take to travel through time, we learn about the limits of gravity, the shape of space-time, the behavior of energy, and the quantum underpinnings of reality itself. Time machines, real or not, push us to test the boundaries of what's possible. They force us to confront the nature of time, not as a simple arrow moving forward, but as a dynamic, pliable dimension that might hold more flexibility than we ever imagined. So while the idea of climbing into a time machine and setting the date for ancient Egypt or the year 3000 might still belong to fiction, the science behind it continues to evolve. Equations are written, models are tested, new theories emerge, and perhaps someday, the wild ideas of spinning cylinders, warping wormholes, or engineered loops in time will move from chalkboards to construction plans. Until then, the time machine lives on, not in iron and steel, but in the minds of those daring enough to question what time really is, and how far we might one day travel through its mysterious corridors. Since the beginning of storytelling, humanity has gazed not only toward the stars, but toward the flowing river of time, wondering what lies upstream and downstream of the present moment. Time travel, as a concept, is ancient. Long before equations and theories tried to bend space and time into shapes that could carry us into the past or the future, people dreamed of such journeys through stories, myths, and visions. From the earliest legends to the most modern films, the idea that we could slip free from the present and walk through time like a corridor has fascinated, haunted, and inspired us. But beneath all the imaginative tales, there's a deeper question. Why does time travel captivate us so much? Why does it resonate across cultures, centuries, and generations? The answer may be simpler than physics. Time travel speaks to the human heart. It is the ultimate what if. It opens the door to regrets, hopes, second chances, and future dreams. If you've ever wished for one more moment with someone you lost, one more chance to say something unsaid, or the opportunity to undo a decision that changed everything, then you've already participated in the longing that fuels the fantasy of time travel. We are creatures deeply aware of time, yet bound by it. We remember the past and imagine the future, but we're trapped in the ever-moving now. Time travel offers us a kind of escape, not just from time, but from limitation, from finality, from the linear march of cause and effect. In fiction, time travel has taken many forms. Ancient stories told of prophets who glimpsed the future in dreams or visions. Folk tales from various cultures describe enchanted places where time passes differently, an afternoon inside a hidden cave, only to emerge and find that 100 years have passed. These stories reflect our earliest intuitions that time is not as steady as it seems. Then came the literary visionaries, like H.G. Wells, who gave us one of the most iconic machines in fiction, a device that could move its passenger forward or backward in time at will. Wells didn't just entertain, he launched a genre. And since then, time travel has become a mirror we hold up to ourselves, a way to explore deep philosophical and emotional questions. Some stories use time travel to imagine better worlds, to escape tragedy, to rewrite history for the better. Others explore the dangers, the complications, the delicate threads that tie every event to countless others. A small change in the past ripples into an unrecognizable present. A trip to the future reveals a world we're not prepared to face. The most powerful time travel stories don't just bend the rules of physics, they examine the soul. What would you do if you could see the moment your life changed? Would you try to alter it? Would you accept it? Would you finally understand it? These questions are timeless because they speak to the inner tension we all feel between our memories and our dreams. And yet, time travel also reminds us that time itself is a kind of gift. Because we can't go back, because we can't jump ahead, every choice we make becomes sacred. Every moment, no matter how small, matters. It passes, never to return, and in that passing, it shapes the story of who we are. The fantasy of time travel lets us explore what we would do with more time, or different time, but it also quietly teaches us to cherish the time we already have. The irony is beautiful. In dreaming of breaking free from time, we often come to appreciate it more. Science may one day offer us strange ways to stretch or fold time. Maybe the theories of wormholes or closed time-like curves will evolve into real, usable technologies. Maybe far in the future, someone will walk through a corridor and emerge in an era they never belonged to. But even if that day never comes, time travel will continue, in our stories, in our imaginations, and in our memories. Because memory itself is a kind of time machine, so is anticipation. So is hope. Every time we look back with nostalgia, every time we look forward with wonder, we are stepping outside the present and touching another place in time. So we continue to dream. We imagine clocks that run backward, doors that open onto yesterdays, and staircases that rise into tomorrows. We wonder what we would say to our younger selves, and what advice our future selves might whisper to us if given the chance. These dreams are not just science fiction, they are human. They come from the same place as love, loss, and curiosity. They come from the part of us that wants more, not just of time, but of meaning. And maybe that's the greatest secret of all. Maybe the true power of time travel isn't in moving through time, but in how we feel time. How we carry the past with us, how we reach toward the future, how we hold each moment in our hearts as it slips away. Maybe time travel is already within us, not in machines or equations, but in our capacity to imagine, to remember, and to dream. As we come to the end of this journey, drifting gently through the possibilities of time, it's worth pausing to reflect not on machines, or paradoxes, or cosmic shortcuts, but on the way time truly unfolds within us, quietly, softly, in the spaces between each breath. Time is often seen as something we move through, something external. But perhaps, in these last waking moments before sleep, it helps to see it differently. Perhaps time is not something outside of us at all, but something we carry inside, woven into memory, into sensation, into the way we experience the world. And perhaps the most profound form of time travel isn't the sudden leap into another century, but the slow, invisible journey we take every night as we fall asleep and drift into dreams. When you close your eyes and your thoughts begin to soften, you're already stepping out of the rigid order of clocks and calendars. The sharp lines of past and future blur. Moments begin to rearrange themselves. In dreams, time becomes fluid. You can move from one memory to another without logic or order. You can experience a lifetime in minutes. You can visit places long gone or people who live only in memory. And it feels real, sometimes more real than waking life. In dreams, you are unbound. You are, in a sense, a traveler through time. The subconscious becomes your time machine, gliding through landscapes that ignore physics, that bend around emotion, that stretch or compress the minutes into entire sagas of meaning and feeling. Perhaps this is the kind of time travel we were always meant for, not the mechanical kind, but the emotional kind, the kind that allows you to revisit a childhood home through the scent of warm air, to hear an old song and suddenly feel a moment from years ago as if it's happening again, to read an old letter and feel the presence of someone no longer here. These are not memories, these are re-entries. The mind doesn't just remember, it reanimates, it reconstructs, and in those moments, the boundary between then and now dissolves. And what of the future? How often have you imagined the shape of your life not yet lived? The hopes, the plans, the what-ifs. Each time you do, you are building something. Tiny futures, soft visions, imagined timelines branching off your present like roots in soil. And even though most of them will never come to pass, they are still real to you. In the moment you envision them, they have weight. They shape your choices. They nudge you forward. In this way, you are not just remembering your past, you are also rehearsing your future, moving backward and forward through a life still unfolding, with every thought, with every breath. The truth is, we are always in motion, not just through space, but through time. We measure it in seconds, but we feel it in memories and dreams, in longings and reflections. Every conversation is a meeting between two timelines. Every goodbye is a step into the unknown. Every decision is a fork in a path you can only walk once. And even now, as you lie here in the quiet of your room, as the noise of the day fades into the hush of night, you are continuing your journey, forward, into rest, into the deep waters of sleep, where time flows differently. Sleep, too, is a kind of time machine. You close your eyes, and the hours slip by unnoticed. A dream begins, and you might spend what feels like days or weeks exploring a world that doesn't exist. Then, just as quietly, the dream ends. You awaken to a new moment, a new version of yourself, changed, even if only slightly, by the passage you've made. And who's to say that this isn't a kind of time travel, not across centuries, but across states of being, from wakefulness to rest, from thought to silence, from presence to release. So now, with the night wrapped gently around you and the world outside slowing to a hush, feel yourself floating just a little, light, unburdened. You've traveled far tonight. Through theories and mysteries, through history and dreams, you've looked forward into futures not yet written, and backward into memories not yet forgotten. And as you settle into stillness, know this: you are always traveling through time. With every breath, you are stepping into the next moment, and the next, and the next. There is no need for machines or paradoxes here, just you and this moment, and the soft, infinite unfolding of time. Let yourself drift now. Let go of questions and clocks. Trust that the universe is still turning, that the stars are still singing their quiet songs across the night sky. Time will carry you forward, gently, without effort. And in the morning, when your eyes open once again, you'll find yourself exactly where you need to be. Rest well, traveler. Sleep has found you, and time, as always, moves on.